It is important to note that the internal energy of a gas, a system of particles, is not equal to heat. Okay, they're two completely different things. Okay, I should mention that knowing what the pressure is, considering a certain amount of particles in an ideal gas, you can figure out what the kinetic energy is of that ideal gas, and you can also then figure out what the internal energy is of an ideal gas, or anything else, because the internal energy, which we characterize as capital U, is all of the kinetic and potential energies that a particle or a system of particles can possess. So we can talk about different kinetic energies, like rotational kinetic energy we've mentioned before. We were just talking about angular motion before. And translational kinetic energy. We can also talk about vibrational kinetic energy. Or there could be different bonds between molecules that give you different potential energies. Okay? And so if we're just talking about a monatomic ideal gas, then the only energy associated with that is translational kinetic energy. So the Ke translational for one particle would be equal to 3/2 kBt. For n particles for the entire system, then that would be 3/2 capital N kBt. And so this kinetic energy will be equal to the internal energy because that's all the kinetic energy there is. Now if you have a diatomic molecule, so you have two particles, okay, they can rotate around different axes. And so because of that, you can have kinetic energy associated with rotation. And that changes this factor out front here. You might get 5/2. If you end up with vibrational, you might get even more. You might get 7/2. Okay? And it depends on exactly what is possible and what you can get with regard to the combinations when you add in all of the kinetic and potential energies. So that's the internal energy of your system. Okay? That is very different from the heat. Because heat specifically is a transfer of energy. Okay? It is an act. Something happens where you end up transferring energy, and that is what heat is. Okay? Heat is not temperature, they're different things. Okay? But heat is an amount of energy given to something, or an amount of energy that is leaving something in the form of a transfer. And that's given the symbol Q. Okay? Q can be positive, or Q can be negative. If Q is positive, then energy is entering the system. If Q is negative, then energy is leaving the system. And I have to make a specific point here about what I mean by the system. Okay, we have a system in contact with the environment, something that is placed in. And you have a transfer of energy between the environment and the system. The system could give energy to the environment, or the environment could give energy to the system. It all depends on which is hot and which is cold. We know from thermodynamics that everything flows from hot to cold, not the other way around. And so, if you end up with a transfer of energy into something, so something was potentially cold, or at a different phase, we'll talk about that in a second, then the Q is going to be positive because energy has been given to that system. If that system instead loses energy to the environment, or to something else that it's in contact with, then the energy would then be leaving the system, it would be negative. Okay? We can characterize this in terms of a change in temperature by thinking about specific heat. So, in this situation, you would be giving energy to a substance in order to actually raise its temperature or lower its temperature. Well, you would give energy to it to raise its temperature, you would take energy from it in order to lower its temperature. So in that formulation, Q, the energy in question here, is equal to however much material you have times something called the specific heat for that material times the change in temperature of that material. So this right here, the specific heat, is different for every material you're talking about. Okay, for water, it's 4,186 joules per kilogram degrees C, which is relatively high compared to other things. That's why it takes water so long to heat up, or for your hot cup of coffee or hot cup of tea to cool down. Okay, it's because of the fact, it's because of how large the specific heat is. The specific heat, if I rearrange this, is a measure of how much energy you have to give to something to raise its temperature. And so, what's measured for water is, say for example, a calorie, a lowercase c calorie. That would be the energy needed to be given to 1 gram of water to raise it from 14.5 degrees C to 15.5 degrees C. So about 1 degree C. Okay? The energy needed to raise 1 gram of water 1 degree Celsius. Okay? The regular food calorie that we talk about is a calorie with a capital C. That's actually a kilocalorie. So it's 1,000 times the energy needed for that 1 gram of water to go from 14.5 degrees Celsius to 15.5 degrees Celsius. So instead, that energy is the amount it would take to raise 1 kilogram of water from 14.5 degrees C to 15.5 degrees C. And the specific heat, this measurement right here that's different for every single material, is independent of how much you have. That's why you can multiply that by the amount of material that's there. So this would be the amount of material that's undergoing your temperature change. Delta T is your temperature change, and Q is the energy that has gone in to raise that temperature. Now, if the temperature is instead decreased, that means delta T is negative, and so this Q here is going to be negative. So that's what I mentioned about the signs before, that if energy is given to this substance, this material, to raise its temperature, that Q is going to be positive. If energy is instead leaving this substance, because it's cooling down, then that Q is going to be negative. Okay? And again, that C is going to be different for every single material. It's going to be different for silver, it's going to be different for gold, it's going to be different for aluminum, it's going to be different for water, it's going to be different for mercury. All of those are going to have different specific heats because they're different chemical substances. Okay? And people do calorimetry using this idea in order to actually figure out what those different specific heats are. And calorimetry deals with the idea that we have conservation of energy. That if you put something hot into a container of something cold at a known temperature and a known mass and had that container be insulated and you let that come to equilibrium, then you can analyze the situation saying that the amount of heat lost by the hot object is equal to the amount of heat gained by the cold object. So Q cold plus Q hot is going to be equal to 0. Okay? So the cold object becoming warmer, because it's going to be in thermal equilibrium with this other hot object that's been immersed in it, okay, that'll be positive because it's gaining energy. The hot object that is then cooling down to be in equilibrium is going to end up being negative. And so adding those two things together should give you 0. So if you have 4 things that are involved, like the example that we had in class, where you have a hot piece of silver that's placed into a a container of water, and that container is aluminum, you have water, and you also have a copper stirrer, then that would be Q of the silver plus Q of the water plus Q of the aluminum plus Q of the copper would end up being 0. And that's all because of conservation of energy. And since heat is the measure of transfer of energy, the energy has to be all accounted for. And so the energy gained by the cold object, or objects, has to be equal to the energy lost by the hot object. And so we can say, once these things are in equilibrium, we know this to be true. Okay. And so we can set that up and we can work that out and figure out the different things that go along with that. Now, sometimes you put energy into a system, and instead of changing temperature, it does something else. And that potentially could be it changes phase. That would be the only other thing that actually would be involved here. So when something goes from a liquid to a gas, or from a solid to a liquid, okay, it first has to actually change the phase. And when that happens, it doesn't change temperature, because the energy you're injecting into it doesn't actually go into changing the temperature, it goes into changing that physical structure. Okay? So, any kind of heat measurement we would have with that can't actually involve a delta T, because the delta T is actually 0. And then once it gets beyond that certain phase, then it can actually then increase its temperature. Once it establishes itself as a gas, then it can go on to take more energy to increase its temperature. Okay? But first it has to actually become a gas from the liquid. Or it has to go the other way, where if you're trying to condense a gas into a liquid, or then take that liquid and freeze it into a solid, it has to actually just keep losing energy in that way. And so it cools down to a point where it's going to become a liquid from being a gas, but then it doesn't change its temperature, it changes structure. The energy lost ends up changing its structure. Okay? And then it can cool down more until eventually it changes structure again into a solid. And so we still talk about the transfer of energy that has happened here, and so that Q is going to be equal to plus or minus m times L. And where m is again the amount of material you have, and L is the latent heat for a material. Latent meaning lying hidden within. And so basically it's a measure of how much energy per kilogram you have to give this object in order to make it change its structure. So you have latent heat of fusion, or melting for each object, which we'll call LF. And you have a latent heat of vaporization, or condensation, for each object, which we'll call LV. And so they're going to be different depending on the different material. So in order to actually make water become a gas, as opposed to staying in liquid form, you have to give it a certain amount of energy per kilogram in terms of latent heat of vaporization in order for it to do that. And it'll be different for the water than it would be for, say, mercury, or would be for liquid helium. Okay? But the key thing here is that you have to give energy to it to make it change its phase, to go from a solid to a liquid, or liquid to a gas. Or it has to lose energy to go the opposite way, going from a gas to a liquid, or a liquid to a solid, and it does so in terms of this form. It still has a Q, it's just that Q ends up being not a change in temperature, but involving the amount of material and whatever latent heat you're talking about, whether it be fusion or vaporization. And the positive here goes along with the increase in energy of the phases going from solid to liquid, or liquid to gas, and the negative means that it's losing energy, so it's going from a gas to a liquid, or a liquid to a solid. Okay. There also would then be a latent heat of sublimation, where it goes directly from a solid to a gas, skipping the liquid part, but we're not going to be getting into that in this class. So we'll be dealing with these ideas in class more, and going on to talk about some more bits of energy after that.